So we have two functions shown here. On the left we have this piecewise defined function f of x, which is defined as the line negative x plus 1. This should be a straight line. Should be a straight line with slope of -1 and y-intercept of +1. And so f of x is defined as this line for x values less than or equal to 1, and for x values greater than 1 is defined as the parabola x squared. You can see that f of x here has a discontinuity at x equals 1. And this is a non-removable discontinuity. And g of x here seems to have discontinuities at every integer value of x. G of x is the greatest integer function, or the floor function. So it's the function where you take an x, and g of x is going to be the largest integer that's equal to or smaller than that value of x. So let's say we took x were 3.5, for example, then g of x would be 3. And this function has points of discontinuity at every integer value of x. So both of these functions have points of discontinuity. It seems like at this function, the limit coming in from the left equals the function value. So the limit coming in from the left at x equals 1 is going to be 0, but the function value is also 0, because remember, f of x is defined as negative x plus 1 for values of x less than or equal to 1. So at 1 it's going to be defined as -1 plus 1 is 0, and that's also the limit coming in from the left. But that limit's not equal to the limit coming in from the right. So for f of x, the function value is equal to the limit coming in from the left, and we call this scenario, we'd call f of x left continuous at x equals 1. So we'd say this is left continuous at x equals 1. Now in this scenario, the limit at every integer value of x, the limit coming in from the right, say let's look at x equals 3, the limit coming in from the right equals the function value at that integer. And the same is the case for other integer values, say like x equals 2, for example. Limit coming in from the right is 2, and the function value g of x is 2 as well. But the limit coming in from the left is not equal to the limit coming in from the right, nor is it equal to the function value. So in this case, the case in which the limit coming in from the right is equal to the function value, we call that right continuous. So we're going to say here that g of x is right continuous for integer values of x. So in general, a function f of x can be described as left continuous at x equals a if the limit coming in from the left, the limit as x approaches a from the left of f of x, is equal to the function value, so is equal to f of a. And it can be described as right continuous at x equals a if the limit as x approaches a from the right of f of x is equal to the function value f of a. Now in this case, on the left, this function on the left, f of x, this piecewise defined function, again, the limit coming in from the left is equal to the function value, so it's left continuous, but it's not right continuous because the limit coming in from the right is not equal to the function value. On the other hand, g of x, this greatest integer function, is right continuous because the limit coming in from the right is equal to the function value, but it is not left continuous because the limit coming in from the left is not equal to the function value. So we've talked about continuity over open intervals. We've gone over functions that are continuous for all real values of x. And we've talked about functions that are both right and left continuous, but we can also speak about continuity over closed intervals. So say we were asked over what interval is the function f of x equals the square root of 9 minus x squared continuous. Well, we know h of x equals 9 minus x squared is continuous for all values of x, because it's a polynomial function for all, I guess, all real values of x. And we also know that g of x equals the square root of x is continuous wherever it's defined, because that's the case for this is the case for x to any power 1 over n, where n is a positive integer. So the square root of x is continuous for all, or wherever it's defined. Wherever it's defined. But where is it defined? Well, this is an even root, so it's going to be defined for all values of x greater than or equal to 0. So we know that g of x is continuous. I'll just abbreviate it CONTIN when x is greater than or equal to 0. Well, great. So then if that's the case, then we know that g of h of x is continuous whenever 9 minus x squared is greater than or equal to 0. The g of h of x is equal to the square root of 9 minus x squared, and that's the function we're interested in. So if we need 9 minus x squared to be greater than or equal to 0, then we also need x squared to be less than or equal to 9. When does this happen? Well, this happens when x is in the closed interval -3 to +3. So by plugging in some points, we can draw a quick sketch of this. So if we plug in -3, we know the value of square root of 9 minus x squared is 0. If we plug in +3 for x, we know the value of 9 minus x squared is also 0. If we plug in 0 for x, we know the value of 9 minus, or sorry, what I meant was the square root. If we plug in -3, we know the square root of 9 minus x squared is 0. If we plug in +3, the square root of 9 minus x squared is 0. If we plug in 0 for x, we know the square root of 9 minus x squared is +3. So the graph ends up, if we plugged in more points, we'd see the graph looks something like this. If we want to comment on its continuity, what we can see is that we want to comment on its continuity over this. We know it's continuous over this closed interval. And what we can see is that, well, it's going to be continuous over the open interval. So we know it's continuous over this closed interval. But looking at the graph, that means that it's continuous over this open interval -3 to 3. So I should say x is an element, is somewhere in this interval. It seems to be right continuous at the left endpoint. So the limit coming in from the right, as x approaches -3, and from the right, that should be a -3 of f of x equals f of -3, which is 0. Remember, the limit coming in for the left is not defined because this function is not defined for values less than -3. So this function is it's right continuous. This means that it's right continuous at x equals -3. And we can see that the limit coming in from the, should be connected here, the limit coming in from the left at +3 is equal to the function value at +3 is also equal to 0. So the limit as x approaches +3 from the left of f of x, the function value at 3 is 0. So this means that this function is left continuous at x equals +3. It's not going to be right continuous at x equals +3 because remember it's not defined for x greater than +3. So it's right continuous at the left endpoint, it's left continuous at the right endpoint, and it's continuous over the corresponding open interval. So we can actually generalize our observation here to say that f of x, any function f of x, is continuous over the closed interval a, b if these three criteria are met. So the first criteria is if it's continuous, first criterion is if it's continuous over the corresponding open interval AB. The second one is if it's right continuous at the left endpoint x equals A. The third is if it's left continuous at the right endpoint x equals B. And that was just a generalization of what we observed here. So here we saw that this function, we knew it's closed, or it was continuous over this closed interval. So we observed, okay, it's continuous over the corresponding open interval. It's right continuous at the left point, x equals -3, and it's left continuous at the right endpoint, x equals 3. That was just one specific case. In general, if these three criteria are met, we can say that this function is continuous over the closed interval AB.